problem on optics. There the question is that there are 2 point sources of light. So point sources which are separated by a distance of 24 centimeters. And these sources are placed near a converging lens. Okay. And that converging lens and the plane containing the optical axis of the lens and the diameter of the lens and the plane which is given on the board, that plane is the same. So practically the aperture diameter and the principal axis, that plane is the plane of this triangle which is given. Now the question is such that in this figure, the location of the sources and their images, that is shown by 4 dots. So you can see that they have given you an equilateral triangle and the centroid of the triangle. These 4 points basically comprise of 2 point sources and 2 of their images, right? So they say that these 3 dots are on the vertices of equilateral triangle and the 4th dot is on the centroid of this triangle. So can you find out the focal length of the lens? So we have to find out the focal length of the lens F. That is the question. Now let's see how can they form this setup. I mean, if 2 of the positions are occupied by the sources and the remaining 2 are their images, then what orientation can the principal axis take in this combination? पहले तो ये सोचना. So let us think on those lines. Let's say these points are A, B, C. अब देखो, I basically think that in this problem there are 2 possibilities. First let us think about the position of the source, S1 and S2. Now there are 2 possibilities. Either S1 and S2 both are lying on the periphery, that is A and B, B, C or C, they are symmetric. So either 2 of these positions are acting like sources and the remaining 2, that is one edge and centroid as the image. So the first possibility, case 1, is one of them, like this is acting like a source S1 and this is acting like a source S2, and maybe these 2 are the images, I don't know, I1, I2 or vice versa. So this is one possibility. Baki, as far as the orientation is concerned, it does not matter that which of them is S1, which is S2. Logically, there is circular symmetry, right? And case 2, in this case, for me, seems to be a possibility where one of them, like if this is the equilateral triangle, A, B, C, and this is the centroid for me, let's say O. Now in this case, I can have one position as the source and one edge rather. Maybe this is source 1, S1, and the second possibility is here, S2. Now we have to think that one of them will be the image, like I1, I2 or I2, I1, kuch bhi likh sakte hain. So this is my case 2. So first thing that I want to find out is which of them is correct. Now let's observe. The first observation that I want to make here is, if S1, S2, and you can understand they are symmetric people, right? S1, S2. So out of these 2, I am saying, let's say this guy behaves like I1. If this is correct, then this guy behaves like I1. And let's say the centroid behaves like I2, or vice versa can also happen. And all of us understand that the question paper setter has not given you the principal axis, right? So first of all, let me try to find out the optical center. All of us understand that the line joining the source point with its image S2I2 and the line joining S1I1, the location where they intersect, that is the optical center for me. This is the optical center. If this possibility is correct, if this is the correct possibility, then this is the optical center. With respect to the optical center, my principal axis can have any orientation. I don't know where is the principal axis, but the matter of fact is, what I'm trying to search is this combination possible here, right? S2I2. Now, one thing is very clear. Whatever is the orientation of principal axis, let's say this is my principal axis, and it is at some angle theta, S2 and I2 are on the same side. And if this is the optical center and this is the source, it seems like this is your object S2 or uska image is this. So it is an erect image, it is on the same side. But we know this property that for a converging lens, if you get a virtual erect image on the same side, it cannot be of a smaller height. I mean, the magnification cannot be less than 1. So my primary issue with this is a virtual image, it is on the same side, and it is contradicting the possibility. I'm not even bothered about S1I1. I understand that with respect to this S1, an inverted real image can be formed here. That's fine. I mean, I don't have any hassles with this. I don't know the distance yet, that this distance is between F and 2F or between for the 2F and beyond. That will depend upon the size. But one contradiction is there. That is one issue with me. Somebody can say, no, sir, there is a possibility that you draw. I'm just looking into possibility and I'm trying to first figure out that which of the possibilities I have to ignore. Then the things can become simple for me. Then somebody says, fine, you have drawn this principal axis like this. Think of a principal axis which is below this line where you have got I2 and S2. Again, I have the same concern. This is at a, I mean, that's not possible that the image is closer in comparison to the source if they are on the same side. So the contradiction holds. So this is not possible. Now somebody says, in case 1 only, another student says, you find you have taken this point as S1, S2, right? I1, I2 have taken like this. So just change it. So maybe somebody says, I will take this point as I2. This is A, B, C, and here I have got my centroid. And centroid I am taking as I1. Now you understand the same philosophy holds again, because S1, I1 if I connect and S2, I2 if I connect, I will have my optical center here. And for S1, I1 only, you can see, I mean, I1 cannot be nearer if it is on the same side. There is a contradiction. So that tells me that case 1 is not possible. So whatever he has said is only possible in case 2. Now, the problem is streamlined now. We have to observe case 2. In case 2 now, fine. So one thing I am clear about, that S1, S2, they will lie like this. And in this case, if I want to solve the problem, I can take any one of them as I1. So maybe this is my I1 and this is my I2. If this is the case, then S2, I2 I connect. It comes out like this. And S1, I1 I connect. It is this. Again, this comes out to be the optical center. This comes out to be the optical center. And now we don't know the location of our... so let's do one thing now, because this observation is clear now. So let us try to sit here and draw all the arrangement. I mean, I just want to rotate this system, S1, I1, S2, I2. So just for the sake of simplicity, I am saying, let me draw it again. So I am taking this as S1, I1. This is the possibility now. This point is S2, and this is I2. And connecting line of S2I2, connecting line of S1I1. This point is now acting like my optical center. This is same picture as that of what I have drawn here in case 2. So now I know this. Now, what is the data given? He wants me to find out focal length of the lens. I'll calculate it. Don't worry. What is given to me in the problem? The distance between the 2 point sources of light, that is given as 24. So I will definitely use that property here. अब इसको use करेंगे. That distance I will use at 24. Now first let me draw the principal axis and finish off the problem. So first of all, I took a general, like I thought this is a general principal axis and it is at an angle of theta. Now with respect to this, you can draw your image like this. Let's say this is the image. This angle is 90 and this is the source again at an angle of 90. That's fine. One thing you need to understand here, this angle is theta, this is theta, because this edge and this edge is equal. So you can see these triangles, these two triangles are congruent, right? That basically means because these two sides are equal and the three angles are also equal. So this side is also equal and this is the principal axis and object is here now. Na? S1 represents the object location and this represents the image. And this length is equal to this. So practically this is 2f. Real and inverted image of same size. That is possible. This size and this size is equal. That is possible only when they are at a distance of 2f. And remember, 24 is the distance. 24 here is the, I will draw here, is this distance between the two sources. So this distance is 24. So 24, 24, 24, right? So I understand, all of us understand that this comes out as, that is 2 into 24 into cos 30, that is root 3 by 2. So 24 root 3 directly. Or so you understand that these values here are 12 root 3 and this is also 12 root 3. I don't know the value of 2f yet. But I am writing one equation now. I am saying twice of f, right? That seems to be 12 root 3 cos theta 2. Remember, I don't know theta yet. I don't know the focal length yet. But by virtue of this, I have got one equation that this 2f should be 12 root 3 cos theta. And that makes my f as 6 root 3 cos theta. That is equation number 1. It is 6 root 3 cos theta. That is equation number 1. Now let me talk about the second image. दूसरा जो image बन रहा है, उसके बारे में सोचते हैं. Now with respect to optical center, I can see here for S2I2, observe it. S2 is this object and its image orientation is somewhere here. I know, like something of this sort. This is S2I2. I want to write one equation for this orientation also, S2I2 wala orientation. That second equation I'm expecting, because with respect to that first set, S1I1, I got one equation, and second equation I want to write from that.
Okay, sir.
And all of us understand here, these values, like ये distance जो है, this distance here is known to us. This is how much? It is coming out as 12. So this value here is 12, and this angle geometrically, that is 90 minus theta. So in the S2I2 combination, right, I'm directly making a statement that if this distance is 12 and this is centroid to the edge, which is given as 24, I've drawn here. So this is 36. So obviously these heights, right, for S2I2 combination, the magnification M in this combination for me is 36 sine 90 minus theta upon 12 sine 90 minus theta. So I can directly say it is 36 upon 12. That magnification is coming out as 3. And now I want to just apply S2I2 combination only. I want to apply the thin lens formula once. So let me write it as this. Both the forms I can write it, whichever way you are comfortable. If you are comfortable with this form, you can write, or you can write the magnification form also. So you can write it as 1 upon m minus 1, that is equal to u upon f. And for the S2I2 combination, this becomes 1 by 3 minus 1, that is equal to f is the magnitude, positive focal length of the converging lens, and u. So u, this being the principal axis, this being the optical center, is negative of 12 sine theta. Negative of 12 sine theta. You can check that. This is the object location. This distance is 12 sine theta. So that basically tells me that minus 2 by 3 is minus 12 sine theta divided by f. So what is the second equation which I am getting? So f from here is coming out as 18 sine theta. And now maybe we are in a better position to answer. So that becomes 6 root 3 cos comes out as 18 sine. So theta comes out as 30 degree, I hope. Is coming out, yeah, 1 by root 3. So it comes out as 30 degree. And f, because I've written as 18 sine, so 18 sine theta, that comes out as 9. So that result will come out as 9. So very nicely framed problem. If you look into the question, it basically talks about elimination of combinations. I mean, if you read the question carefully, if you can judge that what is the possibility, and if you don't presume, there are only two things which you have to be careful about. First, we need to analyze that which possibility is correct. And secondly, we need to understand that that the principal axis in this problem is not one of these axes. It can be at some theta. It may coincide with these axes, but that we cannot assume. So to begin with, you have to take some theta. And the question paper setter can definitely, I mean, point these things. The angle of the principal axis or the focal length. Obviously, in this question, he was only interested in the focal. So I think the analysis of the question would be clear to all of you, right? Okay, let's move on to the next problem for the day. So let me take up the second question. Now in this question, that is problem 120, I am interested in the, so go through this problem. The problem here is to find out the shape of the image. Read the question carefully. The question is, what is the shape of the image that is formed by a converging thin lens of focal length f if the object is a sphere of radius r, which is less than f, and the center of the sphere is at the focus of the lens? There is one assumption while this question is put up. There is one assumption that that all the rays which are starting from any of the points on the periphery of the sphere, while they come out of the object, the sphere itself, the refraction which is happening within, that you have to neglect. So basically what we are trying to say is, if this is my converging lens, right, and I have got an object which is in the form of a hollow sphere, maybe a hollow sphere, right, and the distance here, this is given as f, and it has got a radius r, and R is less than F, that's fine. So all the rays which come out from different points of the sphere, obviously you understand that when we talk about people who are on the left hand side, let's say I'm talking about someone who is here, right? And let me treat this point as my origin. Later, I'm solving this problem in 2D, and later on in the final step, I'll rotate this setup about this axis with some omega. And that will help me analyze the problem in 3D. So I'm more of solving this problem in 2D first. Our interest is to find out the shape of the image. Interest is to find out the shape of the image. And honestly, if we can find out the equation, it will be great. So I will solve it completely. I will write the equation for that curve. So take some point here. So maybe treat general xy. So take some point here, x comma y, which is somewhere here. Yeah. And let's try to find out the image of this point. You know. So what are the few things that we can use while answering? So let me first try to find out. Let's apply simple thing. Let's understand that I want to look into the locus of all the points which are treated as objects and their corresponding locus, which is your image. So by absolute basic, first of all, what I'll think is this coordinate here is maybe minus f comma 0, right? So the locus of points which are acting as object, that for me is the equation of this circle. I'm solving this in 2D first. So that becomes x plus f the whole square plus y square, that is equal to r square. We are considering all the xy on the periphery of this object. Remember, as far as your sign convention is concerned, xy takes care of that. So don't have to, x is obviously negative here. So treat this as y only. Simple. No need to change your system. So treat that as y. Okay. What are other equations I can write? So now I'm concentrating on this point as my object, and I want to simply find out its image coordinates. So I'm saying 1 upon v minus 1 upon u term is x for it with sign convention. That is equal to 1 upon f. So take it as f. Remember, I have already taken f in this problem as magnitude of the focal length. So while writing the further equations, I'm taking care of that. U to ठीक से I have substituted x only. So 1 upon f seems fine. That's the first equation. Remember, this v behaves as x coordinate of the image for me, right? And indirectly, what I'm saying is 1 upon x image is 1 upon f plus 1 upon x. So your x image basically is f into x upon f plus x. I'll use it afterwards. X image is this. Now I'm thinking of finding out the y coordinate of the image also, and then I want to find out the equation of the locus of those xi, yi's, and that locus can give me the shape of the image form, right? So let's try to find out now. Now y coordinate of the image, I'm just thinking about the magnification upon y with sign will give me the magnification here, m. And m, obviously I can report because m for me comes out as v by u there. And remember, x image, x, y image, y. These are the 4 parameters I'm dealing. So u in this equation was actually x. And V there came out to be x of image. So I'm getting this, that y image is y by x times x image. Now there are some simple concerns I have got. I need to find out an equation of y image versus x image. That's what I'm searching for. Y image versus x image. And I think in the same equation which was given, that is, look into that equation, x plus f square plus y square is equal to r square. Observe it and try to convert this equation into x image, y image. So I think you can make those changes, because your x there can be written as xi f upon f minus xi. Observe it. X is xif and f minus xi. So you remove x, you write x image f upon f minus x coordinate of image. Like that. Fine. So I'm trying to eliminate x and y. And as far as this y is concerned, now write it carefully. It has y image into x upon x image. Now that term x upon x image is f upon f minus x image. So practically, what we are saying here is, practically, this equation tells me, I'll solve it completely. It is f xi plus f into f minus xi, right? This term, the whole square, RHS will become r square into f minus xi, the whole square, right? And what about the second term? That is, I suppose, f square y image square. Now just focus on this equation. This will help you out in finding out the locus of image. What that comes out as, and just try to write it. It is f raised to the power 4, this term here, this box, plus f square y image square, and that is r square into xi minus f, this quantity, the whole square. That is what we are. And now if you just try to, compile this properly, you will get your equation. Actually, it comes out to be a hyperbola. So this comes out to be, I'm just dividing everything by, so I'm getting xi, just the final equation, xi minus f, xi minus f, the whole square, upon f square, the square, f square by r, the whole square. So the term that f4, I've divided by f4, and minus yi square by f square, right? That comes out equal to 1. Now this equation for me is a hyperbola, and obviously I'll depict this also. Once I justify that the image is going to lie on a hyperbola, finally, because I'll make the comments here only, finally I'll just say that the curve there is a hyperboloid, right? Because when you will talk of for a sphere, so indirectly I will talk about these peripheries which are rotating about this x-axis with some omega. So my hyperbola will also rotate about the same axis as the axis of symmetry, and that surface which will be generated, that I am calling upon as a hyperbola. And where, how to depict this? So all of you understand that that hyperbola will be, I'm just drawing that now. All the parameters are known. Center of that hyperbola that I know is f comma 0. So the center of hyperbola, that point here, will be f comma 0. With respect to the center, this curve, this is the center of hyperbola. The optical center was 0, 0. And the distance from here, a, right, that is f square by r, f square by r. So at a distance of f plus f square by r, you draw a segment of a hyperbola. And similarly, you have to move on the rear side. So maybe somebody can explain, because r is small, so this value is large. So here I am drawing a large value from the center, which is f square by r, and maybe from this point, I'm drawing the second segment of my hyperbola. Now I am in a position to this. So we understand for sure that the image of this guy will be separated into two segments. Like for these points which are lying here, all these points up to the focus. So as you are moving forward, right? So I will have image points which will be somewhere, maybe from here on this hyper. Remember, as I'm moving here, I'm tending like this, right, up to infinity. For this segment, my image is somewhere here. And as I cross that point, then from infinity, I come back on this curve like this. So as you are moving like here, this curve is somewhere here, somewhere. And as far as the lower segment is concerned, just take the mirror image. I mean, the lower segment of the third quadrant is symmetric to this part, and the segment here comes out to be the lower segment on this. And then what I said, I think all of you understand, that rotate it, you get that hyperbola. So all the parameters can be clearly depicted. And as his interest was only to find out the shape, but I have given you a lot of parameters. Exactly I have defined where will that image lie in the given problem. So I think this will be clear to all of you. Now the same idea that I have taken there, I just try to twist a bit in the next problem. There is a geometrical optics aspect to the problem, and then he is trying to extend that concept to interference. So let's understand what he is trying to say. The problem is like this. There is a converging lens, focal length is f, and it is cut along a plane that contains the optical axis of the lens, and a small black plate of thickness delta is placed between the two half lenses. So he has cut the lens, he has shifted the two segments apart, delta by 2 each. In the middle section, he has filled up a opaque object, blackened opaque object. Now, so if I want to solve this problem, actually I'm interested into the ray diagram. Let me explain what I want to find out here. The lens is somewhat like this, half lens. So there are some fundamentals which all of you know, like this central part is the blackened part, then this segment comes, it has been cut, then this comes out to be my original principal axis, which is not the case now. Now the principal axis is like this, PA1, the principal axis for the lower guy, PA2. These are delta by 2 distances. I have got a source here, right? And just to make ray diagram more practical, maybe I'll show it somewhere close. So there is a point source S, which is located at such a distance, right? And that distance here is P, and P is greater than F. And these are the two lenses for me now, right? So now what he is trying to say is, he has given me a screen at a distance of capital H, right? And this is my screen axis. And his question is that with this setup, how many interference fringes you can observe on the screen? Number of interference fringes you will get on the screen. Delta find, so delta I know, P I know, H is known, lambda I'll use afterwards, and focal length is obviously given to me. Now, just observe that P in this case was twice of F. So, few things which were very obvious for me were like, with respect to this axis, I'm sitting here at a distance of 2F. So, fine, I'll form an image. I mean, I've not drawn this practically. The improportional diagram I've drawn. So, this is 2F here. And delta by 2 is the object size. So, maybe you'll get it delta by 2 here. So, this is your image 1. And similarly, these are the easier points of the problem, like delta by 2 here. With respect to this, I'll get it here, delta by 2. And maybe this is my image 2, I2 location. Now, one thing that all of us understand, fine, if this is here, this distance is fine, like this was 2F. So, H minus 2F. So, somebody can say that when you will observe the pattern on the screen, your fringe width is lambda into that distance, H minus 2F upon this distance between the two images, and that I suppose is 2 delta. That is equation number 1. Now, concern is the number of fringes on the screen. So, first of all, when you look into the flux, the flux, all the energy which is incident on this upper lens,
So,
this, all the energy.
so where did that formula come from?
Which one? This one?
Yes, sir.
This is from the result lambda capital D upon small d. So, from the Young's double slit setup. So, that capital D here becomes H minus 2F now, because this distance comes out to be 2F, and that was H. So, these 2 points, I1 and I2, are now going to behave as sources, and they are going to show or exhibit interference on the screen. This is my screen. Then the distance between the slits and the screen becomes H minus 2F instead of D, capital D. And that small d becomes 2 delta, the distance between the images. Right?
Sir, in the question, in the object distance is not given, Richard. It is just given as a distance P. Then how are we taking it as 2F?
It is given, na? Read it. A point like source emitting monochromatic light of wavelength is located on the optical axis at a distance of P. And the value of P is given, na, 20 centimeter, which is twice of F.
Oh, okay. Sorry, my bad.
Now, all the energy, the light energy, which is incident on the upper segment, like even up to the top, so that will be coming here, na? And it's like all this flux is going to finally end up reaching that point I1. So what we are doing now is just look into the spectrum carefully. The topmost point reaches here, let's say. That's why I'm saying it is improportional. And this guy reaches somewhere here. So this beam, which is effectively reaching this point, finally hits my screen between these points, let's say A, and this point B, A and B. So this segment of the screen is exposed by the waves which are coming from one of the point sources, one of the lenses. And symmetrically, I will achieve the waves. I'll find out those rays which will reach the other point. And then I will try to find out that common segment. So from here, I can show one of the rays like this. right? Which will keep on moving further. This, and the last one, which comes like this, will hit it and reach a common point. So what can I say from the top of by symmetry? I can say this will come like this, it will go like this, it will come here. Somewhat like this. So there the points for A from the topmost point. Let me call this as C and this point as D. And now I am convinced that CD is that segment of the screen which is getting, where we are observing waves, where interference is happening. This is the common segment. The upper section, this was the upper section, right? And this is the lower section, and this is the common section. So this is where you will have interference on the screen. Now, we need to find out the length of this section. If I can find out L here, let me first find out what is the value of L there. So all the distances are known. Now find out what is L there. What is coming out as your L? Because one thing we need to understand here, still the fact that this ray which is coming from this point hits it here and intersects here and goes up. Now remember one thing, this diagram I have drawn, assuming case 1, there are a few possibilities I need to observe in this question. Because I haven't looked upon the data yet. There is a possibility that this complete spectrum that you have got here, depending upon the distance, this point may lie on the lower part also, lower side also. Right? The fact, one thing is clear, that one ray which is directly moving, there is no hassle. What are the values? I will comment on that. Don't worry about it. But as a student, first thing we need to be very clear about is these two signals which are coming from the central part, like this, and this aspect which is coming here, D, we are very clear of this distance BD. And there is a possibility that it is also possible that the second, this blue one which I have shown upon as C, if it lies above the point B, right? So symmetrically what may happen is, this ray will lie below point D. And then obviously BD will be the common section. So I am calling that as L prime. And now I am interested in these two things. Somebody can say is interested in L prime. Another student can say is interested in that value L. First of all, we need to ensure that which is the segment, and that depends upon the calculation. So now I have laid upon everything on the board. First thing is to do the calculation and see which segment you find interference to happen. So just, I'm doing some calculations. While I'm writing those things, find out the value of L and check which one is the larger value. So everything is given in the problem, just there, find out the values. Like I'm writing the expression for L prime. You people can simultaneously think about writing expression for L. Okay, so what is L prime for me? The distances are like 2f, 2f, and that height, there was 3 delta by 2. In fact, I can write from here also. So I'm saying delta by 2 divided by 2f, which was P actually, 2f, that is equal to L prime by 2, L prime by 2 divided by the total distance, and that is 2f plus h, 2f plus h. This term cancels out. For me, L prime comes out as delta by 2f, L prime comes out as delta by twice of f and whole multiplied by 2f plus h. This is the expression of L prime. Let's see what is the value. How much is L prime? Everything will be required, so I need to write it carefully. So 1 millimeter, these terms are given. So 1 upon 2f, that is 20 centimeter, and this is 20 plus h is 50. These many millimeters. So seems like 70 by 20, so 3.5 millimeters. That is one thing, L prime. And fringe width also, let me write. What is the fringe width? Lambda here is 0.5 micron. So let us convert it. So 0.5 into 10 raised to the power minus 3 millimeters, and multiplied by h minus 2f. So 50 minus 20. So 30 into 10 raised to the power minus 2, and divide this by 2 delta. So that is 2 into 10 raised to the power minus 3. So I've written this in millimeters. You find out the value of fringe width here. Remember one thing, our answer can be straightforward. We are searching for L upon fringe width or L prime upon fringe width. As we write the fringe width, we are closing it. Now, the only thing is to check the point where the second blue ray intersects. This is a problem, international problem of NADIG. And there is a very conceptual thing where NADIG has not written anything. I wanted to discuss that point. That is where I am landing up now. The thing is, until and unless you give me the size of the aperture, so I have written this thing, I'll write down the value, I'll take this ratio, I'll get some value 46.7, and then we answer the number of fringes which will be formed. But the problem is, the reason why I have drawn the contrary diagram is, looking into the information, nobody can directly tell until and unless you provide, because ultimately everything depends upon the point where the upper ray hits the screen, right? And this point, the movement of this ray definitely depends upon the size of the aperture, which is this segment, this segment. I know one thing, that the location where image is formed, this is your overall principal. Look into one side. This is the principal axis which I have taken here, right? With respect to this axis, I have shown my image to be formed here. And as far as the flux is concerned, just focus on those rays carefully. We have shown this part, and we have shown everything which is coming from the lens to bombard there. This is the segment I was interested in. Now, what I'm trying to say is, one of the rays which is moving is geometrically well defined, so its point, its location is very well defined. D, I have no hassles. The issue lies with the location of C. And for that, the point there is well defined. Just look into this triangle. You know this distance as such. Observe it carefully. But what I am trying to tell is, there is an extra information which we will need. This triangle, if you try to analyze, this much is known to us. But if you look into this height as such is not given. In this problem, he has never given the size of the aperture. If you provide me the aperture also, you provide me delta by 2, that's fine. You provide me aperture also. So this point will be well defined. And with respect to the axis, I know my well defined point here also. Then it will be very simple. I have to just connect them and I know the position. So generally, while solving this problem, what most of us do, even author has also done that. I won't say mistake, because he is assuming aperture to be large. And under that condition, this ray will keep on turning. And if I assume that this delta by 2 is small and aperture is comparatively large, then this dimension, which on board seems to be large, L prime, actually comes out to be a very small distance. You can see 3.5 millimeter. So geometrically, there is a hassle. Mathematically, doesn't feel like, because for that small distance, this will be small. And these distances are decently large. I mean, in comparison to these angles, this will be a higher angle. So generally, this point crosses B and goes above that point B, and A goes below the point C. And that's why we say that we will not consider the case of L. We consider the case of L prime, and then simply we answer the problem with L prime upon fringe width. You make the calculations. It comes out as 46 point something, about 46.6, I suppose. So you will say that approximately you have got 47 fringes. I mean, 23.3 fringes on the upper side and 23.3 fringes on the lower side. Again, I'm saying, general experiment, if I look into this question, I understand what you are doing. Most of us understand, because this is small and that goes beyond. But mathematically, it is better that you provide this fact that aperture size is large, then there is no hassle, and that is one thing we need to consider in the problem. So you will get your result, problem 122.
Sir, in the calculation of L prime in the equation which we've written, why did we write 2f plus h, sir?
L prime, you want to write 2f?
In the bottom left, sir, the bottom left fraction.
I have simply written L prime by 2 here, and total distance that I have written is 2f plus h. Yeah. And here I have written what? It is delta by 2. Understood. That's perfectly fine. I have just.
Sir, but when we look at the ray before and after refraction, there would be a change in its inclination, right?
No, this is the ray which is passing from the optical center of the lens. It is a thin lens actually. So it seems that it is getting refracted. So it is a thin lens, and I'm passing the ray from the optical center, so it will move undefeated.
Okay, sir. Right.
He says if there is a uniform solid sphere, right? There's a uniform solid sphere, and it has got a radius r. It has got a refractive index of n. His question is, if you put a point source of light inside that solid sphere at a distance d from the center, where d is less than r, he is saying, and generally it doesn't happen, but he's saying there will be a unique relation, unique distance, for which all the rays which are going rightwards from the source actually form a single sharp image. We want all the rays to form a single sharp image which are moving rightwards. We'll solve it by two methods at least. So let me first explain what is the question, right? So first of all, this question is not taking small aperture paraxial ray approximation. So all the results that you know, you cannot use directly here. So you have to go from the scratch, right? So put a source here, S, kept at a distance D, and it has got a refractive index N. Everything is good. So he's saying first of all, we need to understand that what he is trying to say is practically possible or not. He is saying that all these rays, let's take a ray which is hitting somewhere here. This is the normal. It deviates away, it comes out. Because he explains everything that if you read it, what is curious is the fact that the sphere forms a perfect virtual image of the light source. That is the backward continuations of all the light rays starting from the source, refracting at the sphere surface and traveling to the right side of the figure, intersect each other at a common point. So he has explained that. Tell me what is the value of D and where is the sharp image of the light source formed. So looking into what he has said, this is one ray which is moving backwards. Let's say this is the point I, maybe, because if I take another ray emanating from the same point, and this is my normal, and it deviates away, and you extend it back, you will get your image at the same point. So not only these two, remember the complete spectrum, which I'm drawing a plane right now, this plane. So all the rays which are coming to the on the right hand side are forming image here. Indirectly, what he wants to say is these rays which are coming out, outwards from all the points of the sphere are coming out only when they are traveling rightwards just. I mean, that point is quite important because that helps me in writing one equation that if I take a ray which is coming just vertically and with respect to the normal, this is the angle here. If this angle is the critical angle, then it will come out tangentially from here. And this guy should also come here. That's what he wants. I mean, this is the other side, the extreme of the data that he has given. And he wants to cover up the full part. Now, we want to write the possibility. I mean, when is this possible? Achha, if I just use this equation that I have written here, that tells me that sine theta c in this problem, this much was straightforward. It is 1 upon n. Now forget this, 1 upon n. Now let us try to focus. And we also know that sine of this angle here will be d. That is the opposite side, d upon the radius, which is r here. So d will come out as r upon n then. Now, first of all, let me go back to the question again. So forget this equation. I'll come back to the same. First of all, let's understand that all these rays, can they form a single image? And what is the equation that I should write for them to form a single image? Now, there are two ways to look into the problem. We can approach this problem by Snell's law, and obviously we can write the same through Fermat's principle also. So I'll try to first write use the Fermat's principle. Jay has asked a problem on the same this year also. So what I will do is, this is S, this distance is D. I'll take a general ray. Let's say this is the general ray. Let's say this distance is S1. Then with respect to the normal, it comes out, right? It travels some distance, maybe D1. And then I will behave like a lens, and finally it will form an image. Like here is the eye or the observer or whatever you want to say, right? So the optical path length here is like NS1 plus D1. That will be equal to, if I take the second ray within the medium and it travels a distance of S2, it comes out at some angle and it travels some D2, and let me extend it like this. So we understand that for them to form a single image, NS1 plus D1 should be equal to NS2 plus D2. That is my equation number 1. Not only this, I can also say, I can observe this point here. Na? These two rays are diverging from the same point. So geometrically, I see that from this point till my image I, if I write the distance as L1 and this dotted length up to this point, right, from I to this point, maybe this point is A, this point is B. So I, A, I'm writing as L1. So L1 plus D1 should be equal to I to B. I'm writing as maybe L2. That is L2 plus D2. These two equations we can write, one by Fermat and one by geometry directly. And from these two equations, if I eliminate D1 and D2 terms, right? So you are getting NS1 minus NS2 is equal to, that is D2 minus D1, which is L1 minus L2. So practically, it seems like NS1 minus L1 is equal to NS2 minus L2. NS1 minus L1 is equal to NS2 minus L2. So the third statement that I want to make now is, the point is that we are writing these terms for all the possible rays. I mean, I'm not writing this equation for two specific rays. Everyone that is going rightwards with respect to this plane, for everyone which is going rightwards with respect to this plane, I'm writing such equations. And when you will write this equation for continuous points which are differentially scattered, this thing is possible. Indirectly, what we are trying to say is NS at different points star minus L at those points star, that term is behaving like a constant. That constant is not possible for consecutive points or continuous spectra until and unless that constant becomes equal to 0. Otherwise, it cannot be constant. And as I get this point from here, we converge onto the idea that this thing is possible if S star and L star, S and L, we can say general S star and L star, like general S, general L, they follow a relation which is actually 1 upon N. And as you say that the ratio, now S star and L star basically are the distance of the point
So,
on the circle, distance of points,
so why must it be 0 only?
because otherwise it cannot be constant. If you take 2 points which are very, very close to each other and you write the value with from S to the next point, which I can write as S plus ds. And similarly, I can write the next point as L plus dl. And ds and dl are both tending to 0. So your expression being equal indirectly tells me that that expression itself is a constant, because ds and dl, they are not going to be 0 as such. So, and now this is happening for all the consecutive points. It's not happening at one location. It is happening at every location which is consecutive. So whatever funda I will give for 2 consecutive points, the same I'm going to copy paste for the next 2 and so on and so forth. And that is very interesting result actually. Once I get this result, indirectly I land up on the concept of Apollonius circle, which we have studied in potential also. Because what we are now trying to say is that the fact that this is a circle, now we are coming, so Apollonius circle converts into Apollonius sphere now in 3D. And what we are trying to now say is that basically these 2 points, S and I, are 2 fixed points, and the locus of those points such that the ratio of distances from these 2 points is a constant, which obviously is the given circle or the given sphere for me. I mean, these 2 points are those 2 points for which the ratio of the distance on the periphery of this circle, which in 3D is a sphere, is a constant, and that constant is 1 upon N. So once I land up there, that this ratio is a constant, I can use this twice to report my desired data, like 1 by N. I'll write it with respect to the 2 extremes. If you give me the radius, right? So S star with respect to this point. So I'll write it as what? D plus R, and the same point with respect to I. So remember, this distance as such is R minus D, this radius as such is R, and this location outside, call it some new distance maybe some P, call it P. So D plus R upon L star, that L star will be P plus 2R. P plus 2R. And similarly, I can say 1 upon N is also equal to, now with respect to this point, now if you write S star, that is R minus D, and with respect to this, if I write this, since that is P. So these are the two equations which I can write to find out P. I have already proved this. And obviously, D there was known to be. So, I mean, they are basically one and the same, whichever way you interpret. You take any one of them and utilize it with the first equation that I have written. That serves the purpose. This and the fact that it becomes a Apollonius circle or Apollonius sphere, and from that, any one of them finally leads me to the location of the image. It's a unique combination. I mean, when you use this fact that this has to remain constant, the problem is, let me explain again. The problem is, if you go to the subsidiary position, then the differential position close to this point, that guy, his ns minus L cannot be equal to the previous one until unless that value is 0. The issue is, these are continuously scattered points with continuous variation of S and L. I mean, every next differential value is possible there. So you are saying it is constant for all the points. That means indirectly you are saying that that constant is 0. Very nice idea-based problem. And same thing which you have written here, that can be analyzed again by geometry through the Snell's law also. Maybe in the next class, I'll try to, analyze this problem by method 2 also for all of you. So just give it a thought by method 2, and I'll take up that idea in the next class. Go through these problems. They are more of qualitative problems, which are definitely helpful in some, if some higher order questions come in JEE Advanced, and definitely in Olympiads also, they will be helpful for all of you. So I'll see you with more subjective problems in the next class, and take care of yourselves. Bye-bye.